Hello friends. So in continuation with previous videos on sheet pile, let's see today anchored bulkhead. So we are going to see the anchored sheet pile, or it is also known as anchored bulkhead. So when the height of the sheet pile is greater than or equal to 6 meter, we normally go for anchored sheet pile. The reason being, we can arrest the deflection of the sheet pile, and the cantilever sheet pile, the deflection is going to be too high if the height is going to be increased further. So we can see what is the anchored sheet pile. You have a sheet pile. Let's say this is the sheet pile which is embedded into the ground. So this is the ground, and you are going to have the backfill here, and here you can, at certain height, you can provide a anchor rod with dead band, or you can have micro piles over here. So this is called anchored anchor rod. So this anchor rod is going to arrest the deflection considerably. If you see the analysis, we have got two methods. One, the analysis of anchored bulkhead is given by free earth support method. So let's see this, and another is called fixed earth support method. So what is this free earth support method? Here, the deflection of the anchored bulkhead is going to be like this. So you can just see that the deflection pattern is like this. This is the deflection pattern in free earth support method. This is the reflected pattern, and the deflection at the anchor rod is going to be 0. So this is how your anchored sheet pile is going to deflect. Now, if you have the cohesionless ground over here, let's say this is the cohesionless ground, and the backfill that you are going to use is also granular in nature. This is also cohesionless backfill. So this kind of sheet pile with the anchor rod is called anchored bulkhead. So what would be the pressure distribution? How will you calculate it? The properties of this soil is known to you. The unit weight, gamma, is the unit weight. So that it is required and another is phi. That is called angle of shearing resistance. And here, uh, below the dredge line, the dredge line, and below the dredge line, the properties phi as well as gamma both are known to you. So we are interested by using free earth support method. Let's calculate the pressure distribution below the height of the wall. Let's say this total height is capital H, and the depth of embedment below the dredge line, as usual, we can take it as capital D. And this anchor rod is provided normally 1.1 to 1.5 times D, and this is, let's say, this is the small h. So we want to draw or calculate and draw the pressure distribution diagram. As we have seen in cantilever, here also we are going to do it. So first thing this, so this is the first part, and the second part is to calculate the maximum moment. And the third part is calculate the depth of embedment. So that's our objective. You will have to, using free earth support and the deflected pattern you have seen it. So let's draw the pressure distribution diagram. From the deflected pattern, you can see that here it is going to be active pressure. Here, this side, it will be active, and this side, it is going to be passive in nature. So it's a combined effect below the dredge line, active and passive both. Hence, the pressure distribution is going to be quite interesting. We can see it. Let's draw. If I draw the pressure distribution, dredge line, the height, as already explained, is capital H, and the rod, anchor rod, is provided. This distance, we can take it as a small h, right? And knowing the unit weight, what would be the pressure distribution? Let's say the is completely dry. So here the pressure is going to be for phi, given value of phi, you can calculate the active earth pressure. So this is going to be active. So here at the bottommost point, the lateral pressure at this point will be active in nature, and that is going to be equal to K into gamma into H. So that's the pressure distribution. Now, if you go below the dredge line, you can see it is active and passive. So now the combined effect is going to be there. And the pressure distribution, I have already explained to you that you know the active pressure. Here, you know the passive pressure. How to calculate the passive earth pressure, that you know it. And therefore, the net effect is going to be like this. So this is the passive pressure. So the passive pressure here, this distance, we can take it as A, and this is the pressure. We can call it as P at dredge line if this is point A, this is point B, this we may call it C, we may call it as D. So different any nomenclature. So this is equal to P at C. The active earth pressure PA at C. So this is the active earth pressure. And therefore, the here the slope of this line is equal to, you can always find it out. Here, this one is going to be, therefore, if you want to find out A, it will be active earth pressure at C divided by this. Now it is going to be both active and passive. So it is going to be K prime, where K prime is the difference between passive earth pressure coefficient minus active earth pressure coefficient into gamma. So this A is given by this expression, P A at this point divided by K prime into gamma. So the slope of this particular line is going to be one vertical, the horizontal is going to be K prime into gamma. So the slope for one vertical, it is going to be K prime into gamma horizontal. Right? So if this distance is taken as y from B to D, if this distance is taken as capital Y, then what would be the pressure, passive pressure at this point? It is going to be combined effect of passive and active, so it becomes K prime. Now, for one vertical, it is going to be K prime into gamma. So, for Y vertical, it is going to be K prime gamma Y. So, this is the pressure. So, friends, you are in a position to draw the pressure distribution, and this is the pressure distribution. This is the pressure distribution. So the lateral pressure distribution over the anchored sheet pi have been shown over here, and it is quite simple. Now, having known the pressure distribution, what is this force? The force, because there is going to be zero deflection over here, the anchor rod is going to exert a tensile force. It will pull it. So that force is called F, or F in the anchor rod. So you can call it FA also. So that's the kind of forces. Now, if you can find out the area of active earth pressure, that is A, D, and let's say this is C, C1. So we can find out the area of A, D, C1 complete, and let's say the resultant of this is P, active. So that is the PA is the active force. So PA is the resultant of active earth pressure diagram, which is given as A, D, C1. So we can easily find it out, the area. And this diagram, below point D up to B, it is going to be passive earth pressure. So this is going to be a force like this, and this force is going to be equal to, it is the net passive force, so I can say RP. And this RP can be calculated. Half into base is already known to you, isn't it? Multiplied by this height. So if you multiply it, it will be y square. So magnitude of both PA and RP being known to you, you can apply the conditions of equilibrium. So friends, if you apply the condition of equilibrium, you can write it like this: sigma FH, the algebraic sum of all the horizontal forces, must be equal to 0. Therefore, the PA, it is the active thrust, is acting towards the left, and minus the force in the anchor rod is acting like this, minus RP must be equal to 0. Now this is known to me in magnitude, as well as the location is also known to you. So let's say the location of this PA is at a distance Z bar. So that is also known to us. We can find out the location of this with respect to the anchor rod. And here RP is also known to us in terms of y. Therefore, we can write it, PA is going to be half into, PA will be half K gamma H square, that is the area of this one, plus what is the area of this is going to be the area is going to be K. This is also triangular, so half. This is going to be K gamma H multiplied by A. This is the magnitude of the force. So H plus A, or you can write it other way around. Fa is not known to us. Minus Fa minus Rp is already known to you. Half K prime gamma y square equal to 0. So one equation, you get it like this. Now H is known to you, K is known, gamma is known, A is known, you have already calculated A. Fa is not known, Y is not known. So one equation you are getting over here. Another equation that we can always calculate is the moment about the anchor rod. Here, we will have to calculate the algebraic sum of the moment about the anchor rod. So if this is A, B, C, D, let's say anchor rod is provided at the location E. So sigma m at E, that must be equal to 0. So now the magnitude PA is known to us. So PA multiplied by Z bar will be the moment about the anchor rod, and this is going to be clockwise in nature. So minus PA into Z bar. Now the another force is RP, and therefore you can say this is going to create anti-clockwise. So plus RP multiplied by, now this is going to be, this force location is 2/3 of Y. So 2/3 of Y isn't it? Plus A plus this height. So this height is going to be H minus H plus H minus H. Now H is known. This is also known. A is known. But Z bar is known. This must be equal to 0. But Y is not known. So this gives you another equation. So friends, you have got these two equations, and these two equations help you in finding out the value of Y. Therefore, solving the equation 2, we get the value of Y. Once you get the value of Y, naturally you are going to find out the depth of embedment will be Y plus A. So the depth of embedment can be found out very easily for anchored sheet pile, and then you can provide D provided will be 1.3 times D calculated. So whatever D comes out from the calculation, increase it by 30%, and that is the magnitude of the depth of embedment. Now, so far as the maximum moment is concerned, the maximum moment, as you have seen in cantilever sheet pile, here there is going to be an additional force over here. So PA acting this way and FA acting this way. So the point of zero shear force or the location where the shear force is going to be zero is going to be between this C and E. So the shear force location, zero shear force, the location where shear force equals to 0 will be between point E and point C. So that can be easily calculated. Let's say that height is, let's say, at a height, say, H1, this is the location where shear force equals to 0. Then we know that the shear force here can be, H1 can be found out. So at H1, the pressure at H1, the thrust, the magnitude of the active thrust can be calculated. Active earth pressure will be this K times gamma into H1, and therefore the total active thrust, so total active thrust between this point E and C will be how much? Half K gamma H1 square. So you know the magnitude of this one, if you see the force acting towards the right hand side above that point is going to be FA. So FA is acting like this is acting like this. Therefore, half K gamma H1 square minus FA equal to 0. Having got this value of FA from the equation 1, we already know the magnitude of FA. Therefore, H1 is calculated. So H1 is the point where shear force is equal to 0. So this is the point shear force is 0. And therefore, the maximum bending moment at H1 can be computed, and the maximum bending moment will be Fa multiplied by the distance between these 2 points, that is H1 minus H, small h. Small h is already known to us. H1 is already calculated. So this is going to create a clockwise moment, plus this is going to create an anti-clockwise moment, and the magnitude, the thrust is half k gamma h1 square multiplied by the magnitude at this point will be at h1 by 3. It is a triangular variation. So the magnitude, all the quantities here are known to you, and therefore you can compute the magnitude of the maximum moment. So friends, this is the complete analysis of anchored sheet pile embedded in cohesionless bed. And the backfill is also cohesionless in nature. So in the next video, I will take a problem on this, and I would like to calculate. There can be water table here. So if there is a water table, water level, then the pressure distribution accordingly you can calculate. So all those things in my next video you will be getting. I think conceptually I have explained you all the pressure distribution, how to compute the maximum bending moment, how to compute the depth of embedment, etc., etc. So this was the objective of today's video, and I think you have been benefited from this. Thank you very much.